Once again, my name is Kemp. I'm with Minnesota Power. It's based out of Duluth in northern Minnesota. Currently, Minnesota Power has a big challenge on their hands, and that is to get 25% renewable by the year 2025. And currently we're doing that with wind, water, and biomass. The area I focus in is biomass generation. We have two facilities with two biomass boilers, and this is a typical way we get our biomass. It starts out as waste from the logging site, then it's chipped up and delivered to our site, dumped in the hopper, and then it is conveyed into our facility. We also get waste wood from paper mills and local sawmills. The facility I'm going to talk about today is the Hibbard Renewable Energy Center. There's a lot of challenges that came with this place. It was built in 1930, has two traveling grate boilers which burn wood, coal, and natural gas. Its main objective is to supply steam to the New Page paper mill, which is about 1/3 of its load. And we're currently to increase our wood burn to 100%. These boilers have also faced many conversions over the years. Back in the 30s, it started out as a coal pulverized unit, then it was switched over to oil, and then now it sits as a wood, coal, and natural gas boiler. We also have some challenges with our workforce. We had 40% turnover just in 2011, and we got more retirements coming in the next 5 years, so as you can imagine, that's been a big challenge. We have a lot of variability in fuel quality. We get very large steam load swings from the attached paper mill. It can be up to 100,000 pounds of steam flow. And we currently have 2 control room operators. We're operating 2 boilers, and management wanted 1. And we also had the issue of high fuel carryover, which I'll explain later. And right here we have a typical biomass boiler schematic. It's kind of similar to what Hibbard has. Here's the traveling grate. This is where the wood's conveyed. It goes back to the back of the boiler on the grate. Grate rolls forward. And you have our undergrade air and overfire air. And when I came on site, I kept hearing the same reoccurring themes and complaints. Can't measure airflow, air controls in manual, need more steam from the mill, it'll never work. We had some poor attitudes going. The wood is too wet, too much carryover, and we need to burn more wood. I also found out there's many ways to operate biomass boilers, and the most popular way at Hibbard was to use lots and lots of air, mainly undergrade air. And what this does is it keeps the grates cool. That's one thing they have to do, is try to keep the grates cool from overheating and creating all kinds of mechanical damages. And then also when they use lots of air, you decrease your chances of the coal fusing together. When you get not enough air and not enough of a bed depth, the coal will fuse together, and then it'll create these plates. And the wood will just go on that plate, pile on there. They call it piling. And then this requires the operator to put on a fireproof suit, grab a rake, go in there and rake out the boiler, and that is not a very popular activity for them to do. There's also the unburned fuel, which when you have a lot of undergrade air, it blows the fuel off the grates. Then it goes out of the furnace as unburned fuel. We're not utilizing any of those BTUs. It just goes into our dust collection system and into the ash. So that's not what we want. And then also header control isn't great. And the mill requires a stable header. We need stable header for our turbines. And if it overpressurizes, they have a vent they can use, which is not real ideal. But our operators are pretty happy about running lots of air. Managers are not so happy. They got steam going out into the atmosphere. They're losing money. The more unpopular way of running the boiler is the hard way. In doing this, you're constantly adjusting the fuel and airflow. trying to build a bed, and then you have this fine balance. If you build too big of a bed, and like I was saying before with the coal, you get the piling. You get busy and frustrated operators. And then with unburned fuel, if they're staying on top of things, they can keep it minimalized. And then also it keeps the excess O2 in check. And the header control is usually pretty good. And then again, they have to stay on top of it. They have to be on their toes. But you get a happy manager out of the deal. Not so happy operators. Then there's burning biomass the smart way. And that's when you let the control system adjust the air and the fuel based off of the pressure demands. Then you don't have as much worries about unburned fuel. Air is automatically adjusted. And the header control is very good. Air and fuel pick up before it's too late. You kind of get the best of both worlds. Happy manager and a happy operator, and you don't have steam going out the vent. We knew we had issues all along, but then the next step was to kind of identify some of these issues. And the first thing we identified was our airflow measurements were difficult to get because of the convoluted duct arrangements we had. We wanted accuracy, but we really needed response and repeatability. And the other major issue is we get a variable heat release from wood and coal. This can vary from the season. It's dry in the summertime. In the spring and the fall, it's wet. You have frozen conditions. And then the different suppliers supply different various qualities of wood. You get hardwood, you get more BTUs, softwood, less BTUs. And then with the dry, dusty wood, you end up getting when the wood dust gets introduced into the boilers, it just basically turns into a bomb. It just explodes, and then you get a sudden pressure increase, and then the boiler has to back off, and it gets kind of ugly. And then wet is just the opposite. It goes in there, and it takes a little while for it to ignite, and then also we get various other issues with distribution and delivery. Some of the other control challenges, we had, like I mentioned before, 2 operators required to maintain these boilers, to make sure they're doing right. And then training the new operators. We had to figure out ways to make it easier to train the new operators with the control system. We also had mechanical challenges. Air dampers were inoperable. Didn't have a lot of feedback coming off of them. They were sticking, and we just weren't able to get the system to control like we wanted it to. We had our list, and then we had to figure out how we were going to accomplish taking care of these items. And we began researching engineering firms and products, and one of the most beneficial things we did was attended a biomass workshop. It was actually put on by Janssen, Combustion Engineering. And we really liked what we saw there. So we investigated further. We actually toured some of the facilities that they installed these systems on, and we ended up awarding them the project. And once they came on site, they started by looking at our existing system. They began to do a computer-based modeling on what we needed, and it revealed that we needed a new overfly air system. So what we did is we installed a state-of-the-art overfly air system. It has these high-velocity air nozzles on them, which are above the grates, and it gives us a good interlaced air coverage over above the grates. Also, they addressed the airflow issues with their improved duct designs. We were actually able to get airflow measurements where they needed to be. And we also added airflow devices that provided repeatable results. And they had heart diagnostics and various other features that we could take advantage of. And the same goes true for the air damper actuators. We got them in better locations, better dampers, and then we had better position feedback. So we were able to take care of a lot of advantages. Once we had all the mechanical and civil engineering that took place, they had all their part taken care of. Next, we had to figure out how to tie it all in together. And also at that same biomass show, we had Emerson was presenting a product there, which was called the Smart Boiler. And what it was, for us it was a logical choice. They partnered with Janssen. We already had an Emerson Delta V system. We were confident they would know that system, being that was from Emerson, so we decided to go with them. And we began installing this smart boiler technology, which is an integrated solution of software and hardware. One of the nice key features of it is it has an intuitive dashboard graphics, which made it easier to train new operators. The pattern recognition, as Harvey pointed out earlier. And then another major issue is the fuel cost optimizer, which utilizes Delta V's Predict Pro, Model Predict Pro optimizer. The optimizer does is it allocates the 3 fuels based off cost. For those that don't know about model predict controls, one of the folks from Emerson once explained it to me as kind of a road. I don't know if you can see this. This is one of our lovely roads in northern Minnesota this time of year. You can picture yourself driving in a car, and you're driving along the road, it's icy, and you see a corner coming up ahead. So what you automatically do is you start backing off on the gas, maybe applying some brakes, because you know if I go too fast into this corner, there's a good chance I'm going to ending up in those trees maybe, or rolled over, possibly hurting the car or hurting yourself. And that's similar to what the technology that Model Predict Control does, but it does it based off of previous history and using models. Next slide here. This kind of shows how it works. Control variables in our case would be the steam header pressure. The process models would be previous history, and it's all compiled into this Model Predict response, which sends its signal to the LP optimizer, which looks at fuel costs. In our case, we set wood to be the cheapest fuel because we wanted to optimize and maximize the use of our fuel. And then we have the constraints. And the constraints, back to the road example, would be kind of icy roads. When you have icy roads and you're driving, you automatically know you have to be more cautious and aware of the situations that you have going on around you. In the case of a boiler, would be the furnace draft. You don't want to have the boiler run past the furnace draft, overpressurize. So once it sees that the pressure is coming up, it starts backing off before it gets too late, and you end up tripping a boiler. Then from here it goes to the move planner, and then the manipulated variables would be the fuel controls and then the air dampers. So what we ended up with was full automatic control with the fuel and the air working in harmony. We had the undergrate, overfire air, and gas burner air working in cascade to maintain the desired excess air in the boiler. The fuels are all coordinated in cascade control, and then we have the constraints to address process limitations. These constraints can be applied selectively. Also, we had a feature in there added for the operators. If needed, they can adjust fuel limits and biases. For example, if slug of wet fuel comes into the boiler, the operator can proactively push some undergrade air to maybe help burn it off. And then once he sees that the fuel's burnt out, or the pile's burnt off, he can return the bias back to 0. Here's an overall schematic of the boiler controls. The plant master, this would be this is basically the boss of the whole scenario. This is where the pressure is brought into, and then it delivers its signal to both boilers. Each boiler has a boiler master, and then from there it determines how much wood, how much air, how much coal automatically based off the operating scenarios. Now we get into graphics. Here's the original screen. Kind of as Harvey pointed out, right now there actually is some issues going on, but you really can't point out, you really can't see anything right now from just by looking at this. Here's the screen we ended up moving towards, and as you can see. Top dead center on here, that means the pressure and the set point are all, or the PV and the set point are all matched up. Everything's good. And then here you can see we're starting to deviate a little bit on the plant master. And another nice feature is you can see if you're in the wrong mode. Whenever you see this pink here, that means it's in the wrong mode. I believe these are in manual right now. And here's an alarm. That's a advisory alarm. And then they're able to adjust their biases and wood limits right here. Another example of the graphics. Prior to this project, entire air system was operated in manual. Manual intervention was required during steam load demands, excessive carryover due to high undergrade airflows and lack of overfire air. High variability between shifts. We had 2 operators required for the control room. We had very busy graphics. Currently, our air systems operate in cascade. The air adjusts automatically according to demand. Undergrade air is now used to improve the boiler response of the speed load to response to load swings. Fuel remains in cascade and is controlled according to cost priorities, and it's very easy to change. The new Janssen overfire air system is coordinated. The new dashboard graphics have really caught on. It's taken some time, and it was a tough sell, but we got people on board, and everyone seems to like them. We were able to go from 2 control room operators to 1, which made management very happy. And the big thing is we have a control solution in place to help us reach our goal of getting to 100% wood and set us up for future EPA regulations. So in summary, boiler operation was in manual and inconsistent. The boiler is now operating in full automatic with improved load response. And probably the biggest key takeaway was this partnership that was formed between Minnesota Power, Janssen, and then the Emerson Industrial Energy guys, which resulted in a boiler-specific solution. They've been very good, the continued support. They stand by their product, and we're continuing working with them to this day. So it's been a very good experience for us. And I believe those getting held for the end here.